All right, so today is our last lecture. What I'm going to do today is I'm going to start talking about the binomial coefficients. Um, this is section 6.4, so chapter 6, um, section 4. So this section, since I can't give you homework on this and have you turn it in and have it be graded, Um, I can't really put material that's only from this section on the final, so the pressure is a little less here. But the actual tools that we are going to use are exactly the choose notation that we introduced in 6.3. So on the other hand, it's a good idea to pay attention to this section because it gives you another way to think about the choose notation and combinations. Okay, so the first thing that I want to talk about is the following. I want to do an example first. So start, oh, I need to do the timer, I'm sorry. Um, Timer 35 minutes, I guess. Okay. So, yes, what I want to start off with is an example. And what I want to do is I want to find the coefficients of x plus y cubed. Now, of course, I could multiply this out straight away and just write x plus y times x plus y times x plus y and start foiling, right? And I'd get x squared plus 2xy plus y squared times x plus y. If I FOIL this out, I'm going to get an x cubed plus a 2x squared y plus y squared x plus x squared y plus 2xy squared plus y cubed. And if I combine all these terms, I'll get x cubed plus 3x squared y plus 3xy squared plus y cubed. Okay, this is just foiling. But another way to think about this is to go back here and notice I can think about all the ways to get a monomial, which means just one copy of, say, x cubed. How many ways am I going to be able to get x cubed if I choose one term from each of my three pools? Well, if I want to get x cubed, there's only one way to do it. Namely, I'm going to take an x from here, and I'm going to multiply it by an x from here, and I'm going to multiply that by an x from here. So there are no choices that I can make. So what I'm going to write is that from the three baskets, there are essentially no choices that I can make. So 3 choose 0 is going to be the coefficient of x cubed. Now, let me consider instead, how could I get an x squared times y? Well, of the three baskets, I'm going to choose one basket from which to pick up my y. For instance, I could pick the first one, so I'll pick up a y from here, multiply it by an x from here, and multiply it by an x from here. Then that's one way of getting y times x squared. Or I could take an x from here, a y from here, and an x from here. That's a different way of getting x squared y. And then the last way to get x squared y is to start off with x, pick up an x from here, and then pick up a y from here. So essentially what I'm doing is I'm choosing one of the three baskets from which to take a y. So here, this will be 3 choose 1, x squared times y. Similarly, if I want to find the number of possible ways that I can get an xy squared, I can think of that as the number of ways of choosing two baskets. I choose two baskets from which to pick up y's, and I choose the remaining basket to be the one that I pick up x from. So for instance, I could pick y from the first tuple, or y from the first term, a y from the second term, and then an x from a third term. Or I could pick y, x, y, or I could pick x, y, y. In any case, there are three choose two ways of getting the monomial xy squared. And then lastly, if I'm trying to get only y's, then out of the three baskets, I must pick three baskets from which to pick up y's. So I'm going to get 3 choose 3 y cubed. And it turns out that these numbers give us exactly the numbers that we're looking for. 3 choose 0 is 1. There's exactly one way to choose nothing from three options. 3 choose 1 is 3. There are exactly three ways to pick one element subsets of a three element set. 3 choose 2 is also 3 because choosing two baskets to single out is the same as choosing one basket to single out. And lastly, if I am taking a three element subset of a three element set, there's only one way to do that. So I actually pick up the exact right coefficients, a 1 here, a 3 here, a 3 here, and a 1 here. Okay? So with this example, we can then generalize this immediately to the binomial theorem. Which is just a generalization of this for arbitrary powers. So the binomial theorem states the following. X plus y to the n is equal to the sum from j is equal to 0 up to n of n choose j times x to the n minus j y to the j. Okay, this is just the summation way of describing exactly what happened here. Here I took 3 choose 0 of x cubed y to the 0, 3 choose 1 x to the 3 minus 1 y to the 1, 3 choose 2 x to the 3 minus 2 y to the 2, and 3 choose 3 x to the 0 y to the 3. Okay, so this is just a generalization of that. And the proof is as follows. So all terms, if you forget the coefficients, all the terms in x plus y to the n are of the form x to the n minus j y to the j for some j with 0 less than or equal to j less than or equal to n, right? This is just saying the coefficients are in front of monomial terms, and all the monomial terms look like this. I know that the total power on any of the monomials is going to be n, so I pick some power for y, and then I fill up the remaining powers with powers of x. So to get a term of the form x to the n minus j, y to the j, we must choose n minus j, choose n minus j terms of x plus y, so there are n copies here. So essentially this is a set with n elements, and I must pick n minus j of them to get x's from. So there are n choose n minus j ways to do this, but by the previous lecture, we know that n choose n minus j is equal to n choose j, right? This is saying the number of ways that you can pick an n minus j element set, like picking an n minus j size subset from a set of size n, is like picking n minus j elements to remove from the subset. But the information of which elements to remove, if I'm removing n minus j elements, that's the same information as including the remaining elements in your set, right? This is like taking a set and partitioning it into two. If I tell you the data on one of the subsets of the partition, you immediately know the data on the other side of the partition. So these two numbers are the same, and thus we get x plus y to the n is equal to the summation from j is equal to 0 all the way up to n of n choose j, x to the n minus j, y to the j. Okay, let's do some examples. So for example, what is the coefficient of x to the 74th, y to the 113th in x plus y to the 187th? Right? So I know that 74 plus 113 should add up to 187, and so this term will appear when oh, you can't see any of this, I'm sorry. What is the coefficient of x to the 74th, y to the 113th in this polynomial? Since 74 plus 113 is 187, I know that this term will appear a certain number of times inside this polynomial. And the answer is just given as follows. Well, it's going to be 187 choose 74, which is equal to 187 choose 113. These two numbers are the same because they're both equal to 187 factorial over 74 factorial times 13 factorial, or 113 factorial, right? In this case, what I've written is exactly this term, but this term, on the other hand, is 187 factorial over 113 factorial times 187 minus 13 factorial, which is 74 factorial. Okay, so huge numbers, probably extremely, extremely big, and I have no way of writing down, I mean, I have no idea how many digits this would be if I wrote it out, but a big number, but we can describe it very accurately, or we can describe it very precisely. Let's do another fun one. And once again, the way that you think of this is you think that you have x plus y, you have 187 of these aligned all in a row, and if you look at all of the foiling together, essentially what you're doing in this gigantic foil is you're picking some, if I'm looking for x to the 74th, y to the 113, I'm picking from the set of 187 possibilities, I'm picking 74 of the linear terms, or the terms of degree 1, from which to pick up an x, and from all the other ones, I'm going to pick up 113 y's. And so I'm doing from 187 choose 74, or from 187 choose 113 y's. I notice that I'm doing the combination, not permutation, because it doesn't matter, like there's no difference between first picking this x and then picking the next one versus first picking this one and this one. Like the order in which I choose them doesn't matter, only which collection I choose from the 187. Order does not matter, so I do the combination counting. Okay, let's do another example. Let's see, what is the coefficient of x to the 12th, y to the 13th in 4x minus 7y to the 25th? Well, by the binomial theorem, this right here is equal to a sum from j is equal to 1 all the way up to, or 0 all the way up to 25 of 25 choose j, and then here I'm going to have 4x to the 25 minus j times negative 7y to the j, right? So if I'm looking for the coefficient where the power on x is 12 and the power on y is 13, then I'm looking for the term when j is equal to 13. So I get the coefficient is going to be 25 choose 13, that's this piece. And then I've got times 4x to the 12th times negative 7 times y to the 13th. And when I write this all out, this is going to be equal to 25 factorial over 13 factorial times 12 factorial times 4 to the 12th times negative 7 to the 13th. Right? This right here is the coefficient times x to the 12th and y to the 13th. This would be a great time to ask if you have any questions. But that's not a very effective tactic these days. Okay, so from this we can actually from this we can derive a lot of very pretty and attractive corollaries and consequences. So corollary, the sum from k is equal to 0 up to n of n choose k is equal to 2 to the n. So first of all, you already know this corollary. Remember that n choose k is essentially counting the number of k subsets of a cardinality n set. So say a set A has cardinality n, and you choose a k element subset. This symbol, n choose k, tells you how many ways there are to choose such a subset. Well, all of the subsets of n appear here, right? Because I'm starting off with 0 subsets of n, and then 1 subsets of n, and then 2 subsets of n, all the way up to n subsets of n. So really, one can interpret this left-hand side as counting up all of the subsets of a set of cardinality n. And as we already discussed, that's exactly 2 to the n, because it's the same as taking a, like the way that you choose a subset of A is, you can think of it as a bit string, where for each element of A, you either choose 1 if that element is in the set, or you choose 0 if it's out of the set. And so there are 2 to the n bit strings, or essentially there are 2 to the n choices that you make, where for each element you either choose whether it's in or out. So one way to think about this is counting all of the possible subsets of a set of a set A of size n, cardinality n. We already know that's 2n. But there's an extremely simple proof, which is that just examine 1 plus 1 to the n. On one hand, this is obviously equal to 2 to the n. On the other hand, by the binomial theorem, this is equal to the sum from j is equal to 0 up to n of n choose j, 1 to the n minus j, 1 to the j, right? Which is exactly equal to the sum from j is equal to 0 all the way up to n of n choose j, because 1 to anything is always going to be 1, and 1 to anything is always going to be 1. So Here, the proof is just finding the right binomial to expand. So that's kind of slick. Wow, look at that. Look at the time fly. Let's do another example that's along similar lines, or a corollary. We can show that the summation from k is equal to 0 up to n of -1 to the k times n choose k is equal to 0. So that is, if you alternate these numbers, if you take some of them to be negative, then when you sum them up, you always get 0. And the proof of this is also really simple. We just find the other right binomial to expand. Well, 1 plus -1 to the n, on one hand, is equal to 0 to the n, which is equal to 0, because n is some positive integer. But on the other hand, by the binomial theorem, 1 plus -1 to the n is exactly equal to the sum from j is equal to 0 all the way up to n of n choose j times 1 to the n minus j times -1 to the j, which is exactly equal to sum from j is equal to 0 all the way up to n of -1 to the j times n choose j. So this thing is equal to this one. Okay. Just some examples of what this is really saying is if we do, for instance, let's do a cubic or something to the power of 3. What this is saying is 1 choose 1 minus, or sorry, 3 choose 0 minus 3 choose 1 plus 3 choose 2 minus 3 choose 3 is equal to 0. And here we know that's true because this is 1 minus 3 plus 3 minus 1 is equal to 0. If we do quartics, then it looks like 4 choose 0 minus 4 choose 1 plus 4 choose 2 minus 4 choose 3 plus 4 choose 4 is equal to 0. And here, this is going to be 1 minus 4 plus 6 minus 4 plus 1. It's going to be equal to 0. This one's a little more non-trivial, right? Here it's kind of obvious because every term is symmetric, but when you're doing an even power, there are going to be odd many terms because you're going from 0 to an even number, and there are odd numbers of those. And then here it's giving you some sort of non-trivial relation on the binomial coefficients, which is kind of cool. And then there are kind of just endless corollaries, like little interesting relations that you can come up with using the binomial theorem. Another simple one is that if I sum from k is equal to 0 all the way up to n of 2 to the k, n choose k, this is equal to 3 to the n. Well, once again, this is just finding the right linear term to expand, right? This is going to be 1 plus 2 to the n. On one hand, it's going to be equal to 3 to the n. On the other hand, by the binomial theorem, this is the same as the sum from k is equal to 0 all the way up to n of n choose k, and then here I'm going to have 1 to the n minus k times 2 to the k. And that's exactly the left-hand side. So you get just for any possible polynomial or any possible thing that you put in here where you break it up into a sum, you immediately get a possibly non-trivial or non-obvious relationship between binomial coefficients and some powers of stuff equaling whatever the sum to the n is equal to. Okay. Next, let's prove another different relation on these binomial coefficients. This is going to be related to Pascal's triangle. Here's a theorem. It's kind of a recurrence relation for the binomial coefficients. So the theorem is that n plus 1 choose k is equal to n choose k minus 1 plus n choose k. There are many proofs of this. There are two that are essentially the same that I can describe for you right here. The first is, this is the proof that the book gives, which is an interpretation in terms of subsets. Let's say T is a subset with n plus 1 elements. How many subsets of T are of cardinality k? Well, on one hand, subsets of a set of cardinality n plus 1 of size k are exactly n plus 1 choose k. But there's another way to count these. The other way to count these is write T is equal to T prime union some element A. So now the cardinality of T is equal to n. In other words, I break up my set T into an n element set and then a 1 element set. And then there are two ways of getting sets of cardinality k from this pair of sets. Either you choose k elements that don't involve the left out element A. Maybe I'll draw a little picture here. T prime, and then little old A on their lonesome. So T is equal to T prime union A. So either you pick a k element subset of T prime and you leave out A, or you pick a k minus 1 subset of T prime and then you include A. Those are the only two types of subsets of T. Either they include A or they don't include A. If it doesn't include A, then all k elements have to come from here. If it does include A, then you're essentially choosing k minus 1 elements from T prime. And that fact that those are the two ways to choose subsets of T exactly gives you this relation. Here, n choose k. This is saying find all the subsets of T prime that have k elements. Or you can choose from T prime a subset of size, k minus 1, and then you include A. So here are the subsets of T prime of size k, and then you're not going to include A. And then here's the number of subsets of T prime of size k minus 1, and then you include A. And then this gives us precisely our theorem. Another way to think about this is to go back to polynomials. And remember that the binomial coefficient is counting polynomials. So consider, or it's giving you the coefficients of powers of binomials. So consider, consider x plus y to the n plus 1, which is going to be equal to, and I'm going to write it as x plus y to the n times x plus y, right? So essentially what we could be thinking about is what n plus 1 choose k counts. So on one hand, we're going to have n plus 1 choose k is the coefficient of x to the n plus 1 minus k y to the k, right? This is exactly what this counts. Well, these two polynomials are the same. So over here, I'm looking for how do I get coefficients of this monomial. And then over here, what I'm going to do is I'm going to say, well, how are the ways that I can get this monomial? Well, over here, in the x plus y sum to the n, this is going to be equal to a big sum of terms, and the only two that I'm interested in are x to the n minus k plus 1, y to the k minus 1, and I know that this comes with a coefficient of n and k minus 1, plus things that look like x to the n minus k, y to the k. And these look like, and this is a coefficient of n choose k, right? And then I have a whole bunch of other terms with different powers. The point is, if I want monomials that look like x to the n plus 1 minus k, y to the k, there are two ways to do that. Either I can start with a monomial over here that looks like x to the n minus k plus 1, y to the k minus 1, and then multiply by y, and then I'll get something of this shape. Or I can start off with a monomial of this form, n choose k, x to the n minus k, y to the k, and multiply by the x, and then I'll get something of the correct form. So the only ways that I can possibly get monomials of this form are either taking this thing and multiplying it by x, or taking this thing and multiplying it by y. And then the total number of those are exactly going to be n k minus 1, x to the n minus k plus 1, y to the k minus 1 times y, and then plus n choose k times x to the n minus k times x, y to the k, right? I'm doing like a kind of a mini foil where I'm only showing you the parts that I'm interested in. But in any case, the coefficient is going to be n choose k minus 1 plus n choose k. This coefficient will be equal to the one over here because they're the same polynomial. So I'm looking at this thing times x plus y, and I'm only interested in the terms that'll give me these powers on x and y. And so there's a whole bunch of stuff that I don't care about. Then there's this term that I get by multiplying by y, and these terms that I get from multiplying by x. Okay, let's do some more things with this. So what this allows us to do is essentially set up Pascal's triangle. So Pascal's triangle. On one hand, what it's saying is that we can make a triangle out of the binomial coefficients 1, 0, 1, 1, 2, oh, I'm not going to have enough space, 2, 0, 2, 1, 2, 2, such that every term is the sum of the two above it. And the sides are always going to be ones. So if I write out, and this continues. So if I write it out this way, this is going to be 1. All the sides are always going to be 1. And then the first two are also going to be 1. And then whatever I get here is going to be the sum of the two above. This is going to be 2. Here I'm going to have 3, 3, 1. Here I'm going to have 1, 4, 6, 4, 1. Here I'm going to have 1, 5, 10, 10, 5, 1, etc. And these are exactly going to be the binomial coefficients. I've only written a small number of them here, but this theorem, where's the theorem? This theorem that n plus k, or n plus 1 choose k is equal to n choose k minus 1 plus n choose k, it's exactly what we're seeing here. 2 choose 1 is equal to 1 choose 0 plus 1 choose 1. If I look here, this is going to be 3 choose 1. 3 choose 1 is exactly equal to 2 choose 0 plus 2 choose 1. And so on and so forth. By the way, Pascal's triangle has been known for way, way, way longer than Pascal. I think the earliest known version of Pascal's triangle was known to the Indians in like 200 AD. And funnily enough, a lot of different cultures name Pascal's triangle after the person who made it famous or who popularized it in their culture. So I think the Chinese, the Indians, the Italians all have different names for Pascal's triangle. Um, and it's super, super old. Um, yeah. How much time do we have left? Oh, none. Okay, great.